All right, let's talk related rates for just a minute. So this is 5/6. Keep in mind as we work our way through this that what we've been doing prior, that rates have to do with those differentials and things changing over time, especially. Okay, so if I want to know how, let's say let's say if I have the variable x and I want to know how it changes over time, I could say that it changes at a rate of dxt. Okay, and that would give me the rate. So just remember that those are talking about rates here. You will have a major quiz over this, probably Friday, maybe Monday, depending on how things go. So stay tuned for that, and I will let you know when that will be. All right, so the easiest thing to do, I think, is to go ahead and just introduce a problem. I'll run you some steps alongside it so you can see how it is we're going to approach these and work these from start to finish. Very, very important concept here for AP Calculus because this will come up so very many times. Um, Almost a guaranteed FRQ for us. So we want to make sure that we have a good understanding, which is why we will really not stretch this out so much as really stress the importance here of related rates. All right, so on page 251 in your book, example number 2, named a rising balloon, and I am just going to type this problem out here for you. If you want to copy it in your notes, or if you just want to say reference page 251, whatever makes it easier for you. But this way, I can kind of reference the words on the screen as I am helping you form and solve the problem. All right, so a hot air balloon rising straight up from a level field tracked by a rangefinder, 500 feet from the lift point at the moment. Oh, come back to me. From the moment the rangefinder's elevation angle is pi over 4. The angle is increasing. The rate, there's your keyword there, rate of 0.14 radians per minute. How fast is the balloon rising? All right, so the first thing I would do as I approach a problem that looks like this, and it can be quite intimidating for sure, is I would look and say, okay, let's see if I can maybe draw a picture. And y'all know I'm not an artist, but I will try my very best. All right, so let's look at what we got here. A hot air balloon is rising straight up from a level playing field. So here's my balloon. Got a little basket on it. Okay, it's rising straight up, yes, from a level playing field. And it says that it's tracked by a rangefinder that's 500 feet from the liftoff point. So somewhere on this ground, right about here, sits my rangefinder, and it is 500 feet from where I lifted off. Okay, 500 feet. From the moment the rangefinder's elevation angle, so here I am and I'm looking up to this balloon. So here's my theta angle. That's my angle of elevation, right? Elevation is pi over 4. So here I'm just going to write theta is pi over 4. The angle is increasing at a rate. Okay, so I told you rate was very important. a rate of 0.14 radians per minute. So what that tells me is that tells me that my d theta dt, okay, this is the rate that theta is changing in terms of the time. All right, so d theta dt is 0.14 radians per minute. Okay, and then it says how fast is the balloon rising. So the first step I would say is, if you can, draw it. All right, so the next thing I want to do is I want to list what I have and what I need. Okay, all right, so let's look at the what I haves first. All right, so I have, and let's give these some names here. Let's say this is A, this is B, and I've got my theta here. I know that theta is pi over 4. I know that A is 500. And again, this is going to be a right triangle because I'm taking off from a flat, didn't it say, a level field. Okay, so straight off, so the ground we're going to assume is making a 90-degree angle here. So I have theta and I have A, and then from the problem I also have d theta dt. So now what do I need? Well, it's asking how fast is the balloon rising. So what is the rate that this height is changing here, okay? And so in feet per minute, and I need to put some labels here, what is the rate there that it's rising? And so what I need is dB dt. Okay? How fast is the balloon rising based on this problem? All right, so I have listed what I have. I know what I need. And I didn't. I'm sorry. This was 0.14 radians per minute. All right. So let's go through and let's think. I need dB dt, right? So I'm thinking, let's think of some way that we can come up with an equation to find, can you think of an equation to find B? Okay, because if I can find B and then I can do the derivative everywhere, right, in terms of t, I might can find dB dt. So that's my next step, is I'm going to try to find an equation that will relate everything. To relate, let's say, what I need to what I have. Okay, and as you look, I have a right triangle, and I need the right here, right? So I guess what I need to say is there any way for me to relate these side links with this angle? And I hope that you could see that this is a trig function, actually. If you think back to your SOHCAHTOA that you first learned in geometry, that actually what's happening here is the tangent of theta is going to equal opposite, which is B, over adjacent, which is 500. Okay, so I actually do have an equation that can kind of relate what I have to kind of what I need by, let's see, I'm going to differentiate this equation because I know I need a dB dt. I have a d theta dt. I've got a theta in here. I've got the a in here. So let's differentiate this equation. So the derivative of tangent. Now here's the tricky part, because when I differentiate, I'm going to differentiate everything with respect to time. So really what I'm doing is implicit differentiation. So I want you to think about that as you go through that. Be very mindful. Remember when we were doing implicit differentiation before and we just had y, every time we'd take the derivative of y, we'd have to follow it with that dy dx, right? So it's the same thought process here. So as I differentiate both sides, well, the derivative of tangent is secant squared theta, but I need to do d theta dt, and it's gonna equal, now think about this not as b over 500, but as 1 over 500 times b, right? And so the derivative of this would be 1 over 500 db dt. Okay, so now the whole entire thing has been differentiated. So now what I really want to do is I want to solve this. I want to, well, before I solve it, or I haven't used yet, what I want to do is plug in what I have, and I want to solve for what I need. Okay, so again, what I have, so I'm going back to that step 2 up here, and I'm just going to plug in, I have secant squared. I know what theta is, right? Theta was pi over 4. D theta dt, again from the beginning, d theta dt was 0.14. And don't put this with as a function of secant. This is not a function of secant. This is actually its own, this is being multiplied here. All right, and then I have equals 1 over 500 dB dt. So I've plugged in what I have, and I need to just clean this up really and solve for what I need. I'm almost done here. Secant squared theta. So remember, secant squared is 1 over cosine. So if you go to your unit circle to pi over 4, you will see that the cosine of pi over 4 is the square root of 2 over 2. And so here I'm squaring it, so I'm 1 over this, right, which would be 2 over the square root of 2 squared times 0.14 equals 1 over 500 dB dt. And I am just going to continue to solve here. So this gives me, and I'm sorry, I'm going to have to go to the next page here. This gives me 4 over 2. 4 over 2 is my 2 over square root of 2 squared. 0.14. Sorry, I had to go back to see what my numbers were. So now times 0.14. Come on. Times 0.14 equals 1 over 500 dB dt. And remember, this is what I'm trying to get alone. So this is 2.14, 1 over 500. And of course, this is an easy solve for you guys now. Multiply both sides by 500. It's 2 times 0.14 will give me my dB dt. And if you put that in your calculator, you should find that this would be This is 1,000 times 0.14, which would be 140. And so now make sure your last step is make sure you interpret, and this is very, very, very important. Always interpret your answer with the correct units. So this was 140, and remember this was that balloon rising up 140 feet per, let's see, per minute. I hope you found that not as intimidating as it looks. So I think I found it easier to show you from start to finish an entire example than to kind of ease into it. So I hope I didn't scare you off too much, but we'll go back now and do a few examples of a little bit easier type thing. Feel free to rewind, pause as you need if you need to go back and watch something. By all means, go back and rewatch the example. But I'd really like to work through a couple of your homework problems with you, maybe two of them, just to show you kind of, if you don't have to set the whole thing up, they'll start you out where you're not setting up the whole problem on your own initially, but really just working through some ways of setting up the equations and solving for certain variables while we're implicitly differentiating there, so it's not quite so bad, so it'll ease you into it. So maybe watch through all the way, and then come back to that first example and see if it makes a little more sense to you with the hot air balloon from start to finish there. So what I want to do on page 255 is work through number 4. And so as I look at number 4, it starts me out with an equation. So it says that the power of an electric current in watts against its resistance in ohms and current in amps is P equals RI squared. So just for your reference here, again, P is in watts, R is in ohms. So we're talking about electrical current and circuits and that kind of thing. And the current is I, and that is in amps. And so the very first question asks me, how is dp dt related to dr dt and di dt? So in other words, what they're asking you for is they're asking you for an equation that is solved for dp dt. And so what I want to do is I want to go through the equation again that's given me, and I want to implicitly differentiate with respect to t for each one. Notice all of these are dt, so I want to differentiate with respect to dt, or with respect to time. So I'm going to take my initial equation, and I am just going to derive here. So dp dt, because the derivative of p would be 1, and then multiply by dp dt. And now the product rule here will come into play, so it will be the derivative of the first, which is just dr dt, times the second, plus the first, which is r, times the derivative of the second, which is 2i di dt. Okay? And in this case, I don't have to do anything else. This equation is already solved for dp dt. If you want to make it look a little bit nicer and clean it up a little bit, of course you can. You can make this I squared dr dt plus 2ir di dt. But that's all we're doing, is we are just getting an equation written for dp dt. Okay? Part B gets a little bit trickier here, and part B asks me, how is dr dt related to, notice that related there, you see why this is related, right? Related to di dt, and then they throw something else in there. They say that if p is a constant. So remember what happens when I have a constant that I'm taking the derivative of. it becomes 0, right? So again, this same equation here, but the derivative of p is now 0 instead of dp dt, but everything else stays the same because there are no other um, p's in the rest of my equation. So everything else is the same. It derives exactly the same way. So I'll just take my information from part A here. But if you read carefully what it's asking you and what we've been talking about, it wants dr dt related. So what that means is I want it solve it for dr dt. What does dr dt equal? How does it relate to everything else? And so all I'm going to do is I'm going to isolate this little piece right here. And so to do that, I'm going to take this whole chunk and I am going to move it over. Okay, and so whenever I move it over, of course I have negative 2ir di dt, and that's going to equal my I squared dr dt. And then what I want to do is divide by I squared. Remember, the goal is just to get, and because this is multiplication, I can just multiply by this one piece. It'd be the same as coming here and saying times 1 over I squared. But I just want to get that dr dt by itself. And so this cancels. And I have negative 2r over I di dt is equal to dr dt. And so now I can tell how dr dt relates back to di dt if p is a constant. Okay? In other words, written in terms of that variable. All right, I hope you're seeing that this is not quite as bad as you thought. All right, let's look at number 7. I want to look at 2 more, number 7 and number 10, and I'll be done. And I'll finish those. So number 7, I start getting into a little bit more, number 7. Okay, I got mixed up for just a minute because it's asking a lot of the same things, and I was losing my mind thinking that I had already done this one. So number 7, I'm talking about my voltage and my amps and my resistance in ohms. So some of the same variables here, but I start with an equation, V equals I times R. V is my voltage and I is my amps. And lost my place in my problem here. R is my ohms. All right. And so it gives me this equation. And then in the problem, it says, suppose that V is increasing at a rate of, so it says V is increasing at a rate of, and when you see that rate, that's what clues you into that differential part, right? Increasing at a rate of 1 volt per second. And I is decreasing at a rate, there's that rate again, at a rate of 1/3 amps per second. Okay, and it says let t be time in seconds. All right, so part A. I start out with A and it says, what is the value So I'm talking value, I'm probably going to be looking for a specific amount, right? What is the value of dV dt? Okay. And what this problem is doing is it's really walking you through the setup like what we did in the very first example where we listed out what do we know and what do we need. This is walking you through part A and B of walking you through what do you know, okay? Because based just on the problem, we know what dV dt is. What is the rate that the voltage is changed? Well, It gave it to us right in the problem. It said the voltage is increasing at a rate of 1 volt per second. So here, dV/dt would be 1 volt. Oh, goodness, if I can spell. 1 volt per second. All right, let's look at part B. Part B says, what is dI dt? Again, given to me in the problem, I is decreasing at a rate of 1/3 amps per second. Well, okay, dI dt is negative because it's decreasing 1/3 amps per second, okay? Nothing too terribly hard. Again, this is just walking you through setting up what you know instead of having you listed out on your own there, okay? Now part C. Part C, we start getting into the related rates and the equations that we need, right? So part C says, write an equation that relates dr dt, oh, no, not dr dt, yeah, dr dt to dv dt and di dt. Okay, so that tells me I got some derivative issues going on, right? So let's go ahead and let's derive our initial equation up here at the top. All right, so I have the derivative, everything again, you look with respect to t, with respect to time. Okay, so the derivative of v with respect to time is going to be dv dt. And then I'm going to use the product rule again here. So the derivative of the first would be di dt times the second plus the first times the derivative of the second. Okay? Now, it asked me how it relates dr dt. So all I want to do for this is I want to figure out how to get the dr dt right by itself. Okay? So solve it for dr dt. Again, I'm going to move this one over. Color looks a little different. I'm going to move this one over, and to do that, I'm going to subtract. So I got dv dt minus, and I'm going to move that r to the front just for the sake of making it look like pretty math, di dt plus, oops, not plus, just kidding, equals I times dr dt. Now, since I have two pieces here, instead of dividing by I think what I'll do is just multiply by 1 over I on both sides and have dv dt minus r di dt. And there's my equation that relates both of them. Okay? Now, if you wrote this as 1 over I dv dt minus r over I di dt, that's fine too, okay? No, there's no specific way that you have to do that. All right, and then part D, we get into what the question would be. Now, understand if you were given this problem, you know, we'd probably be given a little circuit, and I think there's one drawn in your book on page 255. And we'd be given this, and we'd be given the information written exactly this way, and we would be asked what it's asking us in D. It wouldn't walk us through all of this. It would just give us the question, okay? But again, this is just, what do you know? What do you know? Can you write an equation that relates what you need to what you know? Okay, that's all this is doing. All right, so part D says find the rate at which R is changing when, all right, so it's saying what I want is the rate at which R is changing. So the rate at which R is changing is dr dt, right? So that's what I want. And it says given or when V is 12 volts and I is 2 amps. Okay? And then it asks me some more questions about R. It says, is R increasing or decreasing, and explain why. Okay, so let's look. We have an equation for dr dt, right? It's all right here. All this is now is a plug and chug kind of problem. All right, so I have I is 2, so 1 over 2 times dv dt. Well, yep, I have dv dt. That was part A. So that's 1 minus R. Do I have R anywhere in here? Well, I don't, but I do have an equation at the very beginning that tells me voltage is equal to I times R. And I do know V and I do know I, so really I do know R, right? If V is 12 and I is 2, well then guess what? Divide by 2, R is 6. So really I do have R. So this is going to be 6 times, and do I have di dt? Well, yes, di dt is part B, and that is negative 1/3. And so if I do all this, it should give me dr dt. Well, this would be negative 2, so it's plus, so I've got a half times 3, so I've got 3 over 2, which is dr dt. Now remember, my units are very important, yes? So this would actually be 3 over 2, and what was R? R was ohms, ohms per minute. And so then it asked me, is R increasing or decreasing? And I'm sorry, I think this was seconds, wasn't it? Minutes, seconds. And so the answer to that would obviously be increasing because this is positive, right? I'm getting more ohms every second, and not, my ohms are not going down. So if this was negative, it would be decreasing, but because it's positive, it is increasing there. Okay? One more example, and I will be done, I promise. I know the video is getting a little long, it has to be. All right, let's look at number 10 together. Again, this is from your homework. Changing the dimensions of a rectangular box. Y'all will be happy to know I'm going to draw this box for you. I know that y'all calm down. I know y'all are excited to see my artwork again. Here's this a rectangular box. Look at this beautiful box. I think that's a great box. Okay, so I've got this rectangular box, and it says that the edge lengths are X, Y, and Z. Doesn't matter which one you let be what. I'll let the height be X, I'll let the length be Y, and I'll let the width be Z. All right, so X, Y, and Z. So it asked me, and then it gives me some information. So this box is literally changing. If you look, if dx dt is 1 meter per second, that means every second X is increasing by 1 meter. Okay, so my box is growing there. It says that dy dt is negative 2 meters per second. And so since y is my length, that says that every second, while it's getting taller, it's coming in this way, more like a square. And dz dt is 1 meter per second, just like x. And so z is also getting bigger by 1 meter per second there for my rate. Okay, so it says find the rates at which the box's volume, surface area, and diagonal length are changing, and then it gives me some x, y, and z values, and it says when x is, let's see, 4, when y is 3, and when z is 2. I guess I could have looked at that first and drawn it a little more to scale, but that's okay. It doesn't matter. We'll work with what we have. So part A is volume. And so it says, how is volume changing as this rectangular shape is changing, right? So let's think about how we do volume of a rectangular cube, like a rectangular box like this. And so we do length times width times height, right? So just XYZ would give me my volume there. XYZ meters cubed, actually. And so if I'm looking for what I'm looking for, so I've got everything I have here, right? And what I want is dV dt. And so this is already solved for v. So if what I want to do is go ahead and do some derivation here, dV dt equals, yikes, okay? So I have some product rule going on here. I'm going to do the derivative of the first, and I'm going to look at this kind of like that. All right, derivative of the first, which is dx dt times the second. Oops. Plus the first times, and now I have to do the derivative of the second, which I let be yz, right? So here's another product rule. Derivative of the first, dy dt, it's a y by the way, times the second, plus the first, times derivative of the second. Let's see. All right, so now all I need to do is plug in what I know. I know all of this stuff because it was given to me in the beginning, right? So plug and chug. Again, this is nothing more than product rule. It's just kind of, but it's there, okay? All right, dx dt is 1. Y is 3. And z is 2. Plus x is 4. Dy dt is negative 2. Z is 2. Y is 3. dz dt is 1. And let's clean this up a bit. This is 6 plus 4 times negative 4 plus 3 is negative 1. 6 minus 4 would be 2 meters cubed per second. Okay, so how is the volume changing? Well, if all of these are changing at this rate, then the volume of the rectangular box is increasing 2 cubic meters every second. Okay, we'll go through part B now. Part B asks, how is the surface area changing? And this is one you really kind of have to think about and really helps if you have a good picture. All right, so essentially remember I've got 6 different sides to a cube or to a rectangular box like this. And so of those, I've got 3 sets of sides, right? I've got the front and the back, which will have the same area. I've got these 2 sides like this, which will have the same area. And then I have the top up here and the bottom down here, which will have the same area. So really I can just double everything up whenever I do it, right? I can say 2 times, and so the area of, let's say, the red bottom here would be y times z. So I've got 2 of those, plus I need 2 of the green sides here, and the green sides, this is z here, are going to be x times z. And then to that, now I need the yellow ends here, which is going to be x times y. Now, if it makes you feel better to do 2yz plus 2xz plus 2xy, then by all means knock yourself out. I prefer this because remember, as I take derivatives and there's a coefficient in front, I can just leave that coefficient out front and deal with it later. Okay, so I'm going to derive. So ds dt, or dsa, however you want to do, is going to be equal to, because it's asking me how the surface area is changing over time, 2 times derivative of the first times the second plus the first times derivative of the second plus, now go on to the second term here. The first, or actually let's do it the same way we did this. Let's do derivative of the first times the second plus the first times derivative of the second. And this looks worse than what it is, y'all. I don't want y'all to get all freaked out on me. But this is a plug and chug kind of problem. And then I'm going to do derivative of the first times the second plus the first times derivative of the second. And again, I am just going to plug in here and plug in everything I know because they asked me for how the surface area was changing in regards to time. So I got 2 times dy dt from the problem is -2. Z, again from the problem, is 2. Plus y is 3. Dz dt is 1. Dx dt is 1. And z is 2. X is 4. And dz dt is 1. Dx dt is 1. And y is 3. And x is 4. And dy dt is -2. All right. 2 times -4 plus 3 would be -1. Plus 2 is 1. Plus 4 is 5. Plus 3 is 8. Minus 8 is, oh, look at there, 0 meters squared per second. Does this make sense? The surface area is not changing. Isn't that interesting? That as these sides change, my volume is changing, but my surface area itself is not changing. So that's interesting. Okay. And then let's look at part C, and I won't bore you going through all of part C. I'll help you with the setup and let you do some plug and chug with that. Part C asks you for the diagonal, and it tells you that the length of the diagonal is the square root of x squared plus y squared plus z squared and how that is changing. And so I would, again, with my ds dt, and this is going to be a chain rule, so I'm going to do a half times x squared plus y squared plus z squared to the -1/2. Then I want to do the derivative inside, right? So then I want to do times the derivative of x squared would be 2x dx dt plus derivative of y squared would be 2y dy dt. And then the derivative of z squared would be 2z dz dt. And from here, it's a plug and chug just like before. Okay? All right. So what I would like for you to do, and I will post this as an assignment, is on page 255. I want you to do numbers 3, 6, 8, and 9. Okay, so I know I took a long time on this video, but I really felt like we needed that on the front end. And we will spend some more time and do some more of these tomorrow. Okay? Y'all have a wonderful rest of the day.